Hello everyone, this lecture is related to heat conduction in sphere. Heat conduction in sphere. Let us consider this is a sphere and there is some cross-sectional area in the sphere. Suppose this is the sphere and its center is, this is the center of the sphere, this is the R1, the inside of the sphere, this is the spherical section, and this is the R1 and R2 is the outer radius of the sphere, and this is the radial direction, this is the radial direction. So suppose this is the thermal conductivity of the sphere. Thermal conductivity is a constant. So now let us consider the conduction heat transfer in the sphere. So we know that the heat transfer only in sphere, the heat transfer in r direction in 3-dimensional. The heat transfer in sphere is in 3-dimensional, in the r direction, in theta direction, and in pi direction. So we will, for simplicity, we neglect these two terms, and the heat transfer only in the r direction, temperature only function of r. So from Fourier law we know that the heat rate is equal to minus Ka dt by dr is the heat transfer only in the radial direction, and we know that the area of the sphere is 4 pi r square. So when the radius changes, the area changes, and we know that q dot is equal to Ka thermal conductivity of the sphere, which is constant. This is the area of the sphere, delta T is the change in temperature of the sphere, and dr is the change in the radial direction. So putting value of area 4 pi r square dt by dr. Now simplify this, we will get q dot divided by 4 pi r square minus k dt by dr, and q dot is equal to dr by r square is equal to minus k 4 pi into dt. Q dot and dr, r square 4 pi k into dt. Now simplify, take the integral of both sides. At r is equal to r1, at r, suppose this is the center of the sphere, this is radius 1 and this is the radius 2, this is the radius 2, or this is the radius 2. At r is equal to r1, temperature is equal to T1. Suppose at r is equal to r1, temperature is T1. At r is equal to r2, temperature is T2. So at r is equal to r1, temperature is equal to T1. At r is equal to r2, temperature is T2. Now simplify this, we will get, this is constant quantity, is it come out from the integral sign. So this is the heat rate is constant. As we know that the heat enter to this, the heat enter in this direction is equal to the heat leaving in this direction, and there is a constant heat rate is constant. So heat rate is constant. Heat rate in is equal to heat rate out, and it is equal to heat rate constant. So the heat is a constant, there is no generation or no consumption of heat in this section. So heat rate is constant, and further simplify this, we will get q dot r1 to r2 minus 4 pi k T2 minus T1. Now further simplify it, we will get 1 minus 4 5 T2 minus T1 into K. So further simplify by R into take the limit R1 into R2 R1 to R2 4 5 K T1 minus T2. So after putting the limit, we will get by R R2 minus R1 is equal to 4 5 K T1 minus T2, which is 1 R2 equal to 4 5 K T1 minus T2. So further we can simplify it. R2 minus R1 R1 R2 4 5 K T1 minus T2. So if we further simplify this, then we will get, suppose K is equal to 4 5 K T1 minus T2. This is temperature inside at R is equal to R1, and this is a outer surface of the sphere. Temperature is T2, and it is divided by R2 minus R1 divided by R1 into R2 and divided by 1 over 4 5 K 4 5 K is it. This term come to the denominator. This whole term come to the denominator, and K is equal to 4 pi K T1 minus T2 divided by this whole term, and further this is the numerator and it come to the denominator, and the whole term become, this is the whole term, and it is the heat rate. Its unit is watt. Now this is it come to the denominator. So T1 minus T2 R2 minus R1 divided by R1 into R2 1 over 4 5 K is equal to heat rate. So this is the driving force is T1 minus T2, and this is the resistance to the heat transfer in sphere. SP mean sphere, resistance to heat transfer in sphere. So the resistance to heat transfer in sphere is R2 minus R1 divided by R1 R2 into 1 over 4 5 K. This is the whole term is the resistance to heat